Thanks to Alina for pointing that out. All right, two variables. Does it change our process at all?
No.
No. But do check that we are indeterminate. If we just plug 0 in, that is a no-go. So we need to do what here? Okay, we're going to rationalize. So 3x plus h plus root 3x.
So like, but then it's plus 0, so then it's just 3x minus 3x over 8 plus.
Okay, our square roots are all gone in the numerator, so we'll just get 3x plus h minus 3x. And then down here again, don't distribute. Because if you distribute, you're going to have h's in different places that you don't see to cancel. Here, our 3x's cancel and we're just left with h over h. So they also simplify to 1. And I'll write limit one more time. Don't forget, when all this business happens in the numerator, there's still a 1 there. Okay, and now we're not indeterminate. We're okay to just direct substitute. Not indeterminate. So when you substitute, now I'm going to write equals and drop the limit because we're just plugging in h equals 0. And I did forget a root 3x here. Sorry about that. Okay, so this is 3x plus 3x, or 1 over 2 root 3x. You do not need to rationalize that. That's fine. Remember, they want to see your calculus, not your arithmetic. Questions on that one? How'd you do? Everybody rate yourself like with the thumb up, angle, down, like. Okay. Alright, we're going to keep working on these today. Any questions on the homework? Good. Alright, so I do want to address, in fact, pull out your notes from the other day. Like, it was yesterday that we did these. I want to address this section. It was 1.5 down kind of at the bottom left corner. And so we saw that AP problem. It had something, I don't remember exactly what the graph looked like. Something like that. And we had to find the limit of the inside function, and we found that it was whatever number, and then we took that over here. And then the question was, how do we decide which one of these two it is? And the reason we ran into that is because I completely glossed over this part. Sorry about that. So let's maybe write in words what it's telling us. So we know the limit as x approaches c of the inside function is L. That part is normal. I'll say more about it in a second. You're looking at one. It's one of these kind of sheets, but the one for 1.5. Bottom left corner.
Oh, there you go.
Yeah. All right. Yeah. Everybody there? Okay, we're gonna write some notes out. So maybe get a colored something to make it stand out. Okay, and we're talking composite, limits of composite functions. We said find the limit as x approaches c of the inside and then the outside function's value at that point. But for that to be true, this has to be true, and this says that it's continuous there. Okay? So I want to add if the outside function is continuous. then you do that. The problem on, I think it was 1 and 2, both of those AP classroom problems, the outside function was not continuous. So it looked something like this. It was the one over there. Why isn't that one over there? It looked like this. So when we had to go plug into the outside function, it was discontinuous. Remember, that means it breaks in the middle of the function. So we don't have a point of continuity there. In other words, look at this. The limit as x approaches c of the outside is not the same value as if we evaluated at that point. It's broken, discontinuous. Okay? So that's an important, and sorry again about glossing over that with you yesterday, but that's an important piece of this composite limits. So to fix that and to explain the AP problem, I want us to write some notes wherever you want to put them. I'm going to put them here. If the outside function is discontinuous, let's just make it super clear. And there's a lot of explanation that goes into this. So it was kind of interesting to me that the two that were on the AP, number 1 and 2 on the AP problems, you had to have this information. So, okay, so case 1. I actually am going to call these case 1, case 2, case 3. Ready? There's going to be a bit of writing here, so tell me if I need to slow down. If the inside limit is approached from the bottom, and we're going to draw a picture. I'll show you, I'll log back in to the AP and show you the problem again, the two of them. If the inside limit is approached from the bottom, use the left-hand limit outside. And the big idea there is left-hand limit. Okay? So take the left-hand limit of that discontinuous part. Just to be very specific, this discontinuous description has to be at x equals c. Okay? Oh man, I don't want to lose you, but it's technically not even, like, if we're super specific, it's technically at the limit as x approaches c of g of x. So the inside part gives us a value, and then that value to the outside part, if it's discontinuous there, we're using this process. Okay? While you finish writing that, alright, just to remind you what we're talking about. I know you can't see, so I'm going to read it. This is limit as x approaches -1 of f of f. So we have an inside and an outside function. It happens to be the same one in this case. So the limit as x approaches -1 of f. So we're coming in from the bottom. Do you see that? Both lines approaching that point are from below. And our limit is 2. Then we go over to 2 and we see a point of discontinuity. Okay, that's what we just wrote to clarify that title. If for some reason this limit had been 3, well, this function is continuous over here at 3, right? So it's only if the inside part yields a result that's discontinuous. Okay? Well, what we just wrote says this. We're coming in from the bottom, So we need to take the limit from the left-hand side, which is what? 5. And do you remember that that was correct? Okay? Alright. So that's this first case. Take the left-hand limit at the point of discontinuity. Alright, case 2. And by the way, both of those problems happen to be this case. So case 2. I guess before we do that, if you want to draw a little picture of this, just to remind you, we could just write that function. Or some version of it. I'm making stuff up here. Okay? So, coming in from the bottom, from below, however you want to word that, it's coming in there. Okay? And then we'll say left hand limit here. Alright, case 2. We're gonna have to rewrite all this stuff, but so if it's approached from above, what do you think happens?
You do the right hand side.
Yeah. From above. Use the right hand limit. And this is going to be kind of a obscure detail when we get to like April, right? We're going to have to think back to this. So it's good to keep your notes organized where you can find, hey, I have a limit question, I need to go find the limit stuff. Okay, let's just change the picture and something like that. Okay, now we're approaching from above. And now we're going to use the right hand limit. Right hand limit. Okay, well, can you think of other cases? There are actually 2 more. What have we not talked about? So this is the critical thinking part, right? What 2 cases could arise that we haven't brought up?
The left and the right.
Say that again?
If it's coming from the left or the right.
Like directly left and right?
Like if it's not continuous. Oh.
It's okay. You might be onto something, maybe I'm just not understanding.
Horizontal line.
Okay, so if it's not specifically below or above. So it could be horizontal, maybe it's just a linear thing that one side's below and one side's above, etc. Is that what you're going to say?
Got it.
Okay, and then the other case is, what if our original one is discontinuous or has no limit, too? Like, what if the inside function is has no limit? What do you think in that case? What does your gut tell you? Let me sketch a picture. I'll do it in a different spot, but just for the sake of my question. So we're going just to stick consistently with what we've done. What if our inside looks like this? Something like that. And I'm asked to find the limit right here of the inside and take that to the outside. What do you think happens if there's no limit for the inside function?
You go with the answer that has no limit?
So it does not exist, okay? There is no limit of that whole composition if the inside doesn't have one either. So I think in order to save some time on writing, go ahead and draw that picture and say case 3. And the description is this. If the inside, this one's easy, function limit is dne, then so is the composition. Now, these pictures are very shorthanded because I'm not writing limit statements and telling you where to look, right? Please make sure you understand it's not like the left side is always the inside and the right side is always the outside. I'm just kind of sticking with what we've seen for a reference. Alright, and then case 4. Last one. If the inside limit is approached from both sides, like both, let's be specific, above and below, the limit, and we'll just say D and E. Okay. The limit does not exist. So if it's something like this, and again, I'm just making up stuff, right? So it's both above and below. So below and above. Even though the limit of the inside exists, the outside one does not. Okay. That hopefully clarifies that AP problem that we ran into issues on. Are you good? Because you asked that question yesterday, Trevor.
Yes, thank you.
Yeah. Sure.
I was just wondering, because the description did say, once I got it right, it did say the limit as x approaches 3 from the left. So I was wondering why it
Yeah,
was from the left, so that makes more sense.
their description was bad. If you looked, let me know and I can click off of this.
You're good.
We're good, okay. If you look at the first one, this is number 1, which we didn't talk about yesterday. It says the important observation is that x approaches, as x approaches -1, f of x approaches to from below. But then the next one didn't say that, and its wording was weird, so it made sense why, and I just didn't go deep enough into this, so I'm sorry about that.
No, it's alright. We got it down now.
We got it. Now we're experts on composition limits.
Thank you.
Yep. Alright. We need to pick up with fractions, so now you're on the 1/6 insert that I handed out yesterday. So it's the half sheet. It says 1/6 and 1/7 at the top. Yeah. This is from yours, right? Yep. Do you guys remember these kind of problems from algebra or pre-calc? Just not the limit part, but you remember seeing these complex fractions like this?
Yeah.
Okay, so more algebra. We are finishing. Actually, we have 2 more things to talk about in algebraic manipulation. So, counting this one, it's 3. I think this one looks a little bit more algebraic than the next thing we're going to talk about, but what do you think we do? If I just handed you this limit, what is your very first step? Very first step.
Check and see if it is like, what's the word?
Indeterminate. Guys, how frustrated would you be on your AP test if you started doing a bunch of algebraic manipulation and it actually could have just been substituted? Right? So get in the habit of checking if it's indeterminate first. This one is very easy to check. You can call it like just a visual check. You don't necessarily need to write it all out, but most of the time it's just a visual check. So, yes, it's indeterminate, otherwise we wouldn't be writing it here. I think you had one on your homework that was not, though. Or maybe two. Did anybody catch that?
There was one that didn't exist.
No, I'm saying, I think one of them was not indeterminate, but I don't remember. So, just always check for that. So, in order to work this one out, we need to do something with this numerator. So this is combining two fractions with non-common denominators, which, what's the strategy for that? This is a difference, but let's just clean up the numerator in this case. Could this be in the denominator?
Yeah.
Yeah. So when I say clean up, like we have an x minus 1 and a 3. So what do we do for a common denominator so we can actually add these together? Well, this is going to get kind of crowded. I'm going to rewrite so I can have some more space. So we need to give this one an x minus 1 and give this one a 3. Just like you would if there wasn't an x, right? If this was 2/3 plus 5/8, you would just make sure they have a common denominator. Alright? Rewrite your limit. We're still working with inside the limit. And we'll get 3 over 3x minus 3. On that side, minus x minus 1 in parentheses so you don't mess up the sign. And I'm just going to write the denominator one time. So questions on where I got that from? I think I'll center this denominator just because it looks kind of funny. But so questions on where that came from? Are we all good? Alright, what can I do with this? Like, you don't have to, but you can shove it to the denominator. Okay? Huh? Which 3? Okay, good. There's no canceling yet. Yes, you can, but I would like to write another step before we do cancel, but we can't cancel the 3. Not like what you're saying. Here's what I would recommend. If you have a denominator in the numerator, shove it down here with the denominator of the whole fraction. Like that. Okay, and then up here, 3 minus x minus 1 is really 4 minus x. Do I need to do that, or are we following? So I just did this combining like terms here. Okay. So we get 4 minus x. Do you see where to go from there? We're pretty close to done.
X minus 4 cancels.
The way it's written, not
You gotta
well.
factor out a -1.
Yeah, factor out that -1. So look for that. We could, if you're used to seeing that, you could just say, hey, that's -1, or factor out a -1 first. Either way. So let me rewrite again. Factor out that -1 and we'll get x minus 4 in the numerator. Okay. Now we're ready to plug in because we've gotten rid of the indeterminate part, right? The 0, the issue. So now let's write equals -1 over Probably gonna run out of room. Let's make that smaller. -1 over, and we're just plugging the 4 directly in here. So 3 times 4 minus 3, which is -1/9. So when you are given one with complex fractions, it's a lot of algebra. That's why we call it algebraic manipulation. We would algebraic problem only. We wouldn't want to leave that like that. We would probably try to get a common denominator. Okay? So think of common denominators for dealing with fractions. How do you feel about that? Do you like fractions? Okay. Huh? No? Okay.
I did, but
You did when?
like a couple minutes ago before I started this problem.
Before now?
Yeah.
Well, honestly, this entire problem is algebra except for two things. One, the concept of the fact that this is an indeterminate limit. But even if that limit wasn't there, we'd probably still want to manipulate this a little bit. We're not going to leave it as this complex fraction. So that's one thing, and then knowing when to plug the limit in. That's the calculus. Most of this was an algebra problem. Let's go to this 1-6 notes page, please. It's in the stapled packet. We're going to talk about 2 more versions of algebraic manipulation. At some point, you should staple all these notes, or not staple, but make sure they're all together, okay? All the algebraic properties and manipulation stuff. First thing I'm going to tell you about this is you need to memorize it. Because, well, take a look at it. Just looking at this, is there any reason to know what that limit is? Like, can we manipulate it at all? No. Okay, so you need to memorize this little table that we're about to fill out. So, limit as x approaches 0, we see that that is indeterminate because of the 0 in the top and bottom. Same over here. But, excuse me, what we're going to see is that this limit is 1. No matter if sign is on top or bottom, it's just 1. Okay? If we graph this, I might have graphed it. Let's see if I did. No, it reset. Sine x over x. Don't you love how this thing does that? Fraction. Okay, here's a quick tip. TIs, you got to go into window or into zoom and zoom out. Remember that? If you don't like the zoom, you can zoom in and out with the plus and minus button. Pretty cool, right? So there's that graph. Do you see how we're coming up here to 1? It's kind of defaulting to a weird scale, but as we approach 0, the limit is 1. Okay? So now you see it graphically at least. These bottom two, notice the only thing that changes is the order, which is a significant change, but it doesn't actually change the limit value, which is 0. Okay? Memorize those. You probably will never see these by themselves in a problem. In other words, they're not going to ask you to just regurgitate something, right? So look down below at the problems, and I'll show you what I mean. Just take a look at those for a second. You can kind of see the bones of these limits, but they're not exactly the same. So don't force them. Here's how we do it. It would sure be nice if this could look like this, but can I just pull a 3 out of a sign? So this is kind of that algebraic reasoning, like make sure that you're not like overwriting transcendental functions. I can't just be like, oh hey, let's divide by 3 and now I have 1/3 sine x over x. Don't do that. You can't just pull out a 3, right? So here's the process. It's kind of interesting. I hope you like it, because I feel like it's kind of like solving a puzzle. Like, how can I make this look like that? Is kind of the idea. Okay? So we see a 3x inside. So limit as x approaches 0. Excuse me. If we multiply this by 3 over 3, is that okay to do? Yeah.
Yes.
We didn't change anything. Okay. Now we're going to move, and you don't need to write this out every time, but it's kind of like the visual development of this. So I'm just going to separate the 3 on the numerator from the 1 on the denominator. Oh, sine 3x over 3x. Okay? This is in the same form as that. It just has a 3 in it. So what is its limit? It's 1. Okay? So what's our limit now? Oh, not 3. 1. That's 1. So the limit overall is just 3. 3 times 1. Okay? In fact, let's go back to the graph and I'll show you that if I add a 3 in here, 3, see how the graph is the exact same limit at 0. I mean, you can see it's got a shorter period here, but the limit at 0 is still 1. So as long as we make whatever's with x in the sign the same as whatever's with x in the denominator, that limit is 1. So that's the manipulation part. I manipulated this by forcing the denominator to look the same as the argument of the sign. Cool, right? What?
That's bonkers.
Okay. Bonkers.
I'm not a fan.
Not a fan? Okay.
Oh.
Let's do the next one. Look at it for a second. Now I have a sign in the denominator also. Oh, and before we continue, are you checking if it's indeterminate? I forgot to mention that on the first one. Is the second one indeterminate?
No.
Yeah, because sine of 0 is 0, right? So yes, it's indeterminate. So in other words, we can't direct substitute. We've got to massage this a little. All right, anybody seeing a way to do it? Because this is where we're getting into the hard part of limits. These yesterday and today, that's some of the harder stuff of limits. If you're feeling it, that's why. Anybody see a way to manipulate this? Okay, here's what we're going to do. Let me know if this is too small. So we're going to write sine 7x and sine 9x separately, first of all. So again, I want you to think about trying to make these look like these. What do they both need? They both need two things, but what are at least one of them? For this to look like that, what does it need? Okay, so we need an x. Well, I can't just divide by x because that's changing the value, so I need to also multiply by x. In other words, it was the same as 3 over 3, I just did x over x. It's just separated, but it's x over x. Do you see it in there? Okay? So it's looking kinda like this. But, like this one, the sign argument has a number in there too. So what did we do to get rid of that? Or not to get rid of it, but to manipulate it into what we want. Okay? So doesn't this one need a 7 right there? Right? So go ahead and put a 7, but you can't just stick a 7 in the denominator without changing something, right? So where else does it need to have a 7?
In the numerator.
Also in the numerator. So now that's 7 over 7, that's 1, that doesn't change a darn thing. Okay. Second fraction. Sine 9x, we need this to be 9x in order to match this up here. So what can I do to get that? Okay, let's do purple. So 9 and 9. That's 1, it doesn't change anything, but now I have sine 9x and 9x, sine 7x, 7x. It's looking just like this. Everybody good with that? Okay. What is the limit of sine 7x over 7x?
7.
That part is 1.
It's 1.
What is the sine or the limit of 9x over sine 9x? That's 1. And then we have this loose 9 on the denominator. So what's our limit? 7 times 1/9, which is 7/9. Okay? That one was hard to see, wasn't it? It gets better. Any questions on that one? Oh, why 1/9? Maybe I should do this. That is the 1. We have a 9 in the denominator. And then over here, that is the 1. The 7's on top. Maybe if I change the color, that will help. Yeah, that definitely helps, I think, to have the color change with the circles. So if that helps you, do that real quick before we do the next one. Do you want to try the next one? I will give you a hint. The next one, you need to remember one of the trig identities. Do you remember any of those? It's the Pythagorean identity. If that helps. I'm gonna wait till you. Alright, so one thing you can look at is this. We're not going to use it for this case. We could. I think I'm going to do it a little bit simpler way. But let's just make sure that we remember that this is 1. Sine squared plus cosine squared is 1. Remember that Pythagorean identity? Just from right triangles, x squared plus, a squared plus b squared, Pythagorean theorem. So we could potentially try that one, but I want you to notice that this one is a difference of squares. So we can actually factor this. Cosine x minus 1 times cosine x plus 1. In fact, let's name what this is. This is just a difference of squares. Maybe we'll do it 2 ways, we'll see. Keep an eye out for those tricky little buggers. And first of all, we should have checked if it was indeterminate. That 0 right there for sure makes it indeterminate, doesn't it? Okay. Well, what do you notice? At this point, I mean, what do we see?
Cancels.
One of those terms cancel, that one, which saves the day because that one was also indeterminate. And now, what do you see? Are we still indeterminate? Yeah, awesome sauce, I agree. So, algebraic manipulation sometimes includes trig manipulation. If we had used this, so cosine squared x minus 1 would be negative sine squared. Would that have helped in this case? No, because we have this cosine on the bottom. This will come up though, so hopefully you wrote it down as a reminder. You will need to use this sometimes. You'll see an example, probably Monday, I think, of that. Alright. Memorize those and look for them. As soon as you see a trig, I would try manipulating it to one of those. Okay, that's kind of the plan for trig limits. It's not always just a straightforward approach, but that's where your goal is. Can you handle one more thing, or am I overloading you? The last thing is absolute value. You're going to have to write this maybe on the back. So I think I'll talk through one of them and then have you do the other one. So write all that down someplace. I'll give you a second. So remember absolute value. First of all, the graph looks like this. So it makes any value you plug in, it makes positive, right? But we approach that from two sides. So I put in red here, look for two-sided agreement. What does that mean? You should know, but maybe not that wording. So what do you think that is referencing?
Like the output for the input of -2 is the output for the input of +2.
Yeah.
Oh, okay, I can see.
Where you split it to figure out what each side equals.
Yeah, like when you're solving.
Yeah.
We are going to use that actually to figure these limits out. That's not what I meant by the red, but that's exactly what we'll do. So I'll explain what I meant by the red, but here's what these guys are saying. If I asked you to solve an absolute value equation, do you remember how you would split it to a negative case and a positive case? So negative meaning, hey, if I take values left, this is going to be negative, so I have to pull that out front kind of idea. We're going to do that here as well, okay? But what I meant by this, so let's clarify it. Look for two-sided agreement of the left hand and right hand limits.
Makes like they come together.
Well, sometimes and sometimes not. If these don't agree, does the limit exist? No. Just that was our definition, one of them, our condition. If the left and right hand limits don't match, then the limit doesn't exist. Okay? If they, let's just write that, if they don't agree, the limit does not exist. Okay. So here's how that will look. We only are worried about this process for the numerator. Okay? So let's take the left side and we will say limit as x approaches -2 from the left. This is where we pull the negative sign out front. Okay, so negative 5 and x plus 2. Otherwise, we just ignore the rest of it. Okay? Again, we are indeterminate, so we have to do this manipulation to get around that. That's why we're learning this process. Pull a negative out front on the left limit. Out front. Okay? So negative out front, drop the absolute value. If I need to explain that, let me know. I'm assuming that you kind of remember that from algebra and pre-calc like I just reviewed. But if I need to say more about it, let me know. So yes or no? We're good? Alright. The right side, we just drop the absolute value. Drop absolute value. So it's limit as x approaches negative 2 from the right is just 5 times x plus 2. From here, it's smooth sailing. Okay, so this is really just remembering with absolute values to split. That's all. Okay? So we're about done. We're also about out of time. What happens here? These cancel and my limit equals negative 5. Here, these cancel and my limit equals 5. So overall, does not exist. Because those are not in agreement. The left, they're coming in like this, right? Left and right hand limits are different. So that's not too bad. Do we agree on that? If you don't, that's okay, but I don't think it's too bad. It's the same as if the absolute value is in the denominator. Now just run the problem the same way. Like one of these is going to be negative x minus 3. The other is just going to be negative x minus 3. What though should you do with this one? Because I don't see an x minus 3 up there. Factor. GCF out a 2 or a negative 2, either one. So we'll probably come back and look at that on Monday.